assume you can all, okay. I assume you can all hear me and see my screen. I hope somebody can see my screen. I'm sharing that.
Yes, I can see it.
Okay, well, very good. Thank you very much for having me. It's a pleasure to be here, and I hope that you find this interesting, if not entertaining. It's often said that we live in a golden age of astronomy. While this may sound like exaggerated hyperbole, the reality is over the last several decades, astronomy has seen a technological revolution that has transformed the science. This revolution has been led by innovations made possible by development of the high-speed digital computer. Computer-controlled telescopes, CCDs, giant segmented mirror telescopes, and advanced imaging processing techniques remained in the realm of science fiction until a few short decades ago. One of these truly transformative technologies is the topic of my presentation this evening, adaptive optics. Now, I don't expect over the next hour to turn you all into adaptive optics engineers, but I do hope to instill an intuitive sense of how this technology works, and perhaps more importantly, to dispel some of the common misconceptions surrounding this subject. So we have a lot to cover. Buckle up. Let's get started. Start the clock here. Now, as we go through this presentation, there are three things I want you to remember. Of course, we all know that aperture is equivalent to resolution. Small apertures give us a low resolution view. Large aperture telescopes, high resolution, which is encoded in this equation, the Rayleigh resolution formula that we all know and love, which says that the minimum resolving angle is proportional to the wavelength that we're looking at divided by the aperture. Now, through this talk, I'll be pretty much assuming, unless I state otherwise, that we're staying with one wavelength. And for convenience, I'm calling the middle of the visible 500 nanometers, somewhere in the green. A lot of people would disagree with me, but for convenience, we'll just go with that. Now, second thing to keep in mind is any known optical aberration can be corrected with additional optics. Now, any of us that have to wear glasses are intimately aware of this. And the poster child for that is, of course, the Hubble Space Telescope that was sent up into space, was found to have spherical aberration. Fortunately, clever engineers analyzed what that aberration was, designed some corrective optics, and with just about a $250 million delivery fee, those were brought up, installed. And since then, the telescope has performed fabulously. The third thing to keep in mind is any real image can be treated as if, optically at least, as if it were the actual object itself. We can magnify, demagnify, we can distort, whatever we wish, as if we were doing that to a real physical object. So now, the problem, what are we dealing with? Well, our atmosphere limits the resolution we have available here at the Earth's surface, we all know that. And this is due to changes in air temperature, change the refractive index of the air. And that's well illustrated by this picture of the moon with a MD-80, I think it is, flying across the front of it. Now, notice, oh, I have a cat clawing at my leg, excuse me. Notice that the turbulence off the wings are not disturbing the image at all. That's because it is it is the same temperature, isothermal there. But the hot jet exhaust coming out the back very much disturbs the image coming through there. And that's because not that it's turbulent, not that it's moving, but it's at a different temperature. So bubbles of air at differing temperature can act like weak lenses in the atmosphere that deviate the rays coming down from above randomly distorting them as they move through our field of view. So flat wavefronts that are essentially perfect seen coming from astronomical distances are distorted in the last 300 microseconds as they traverse through the Earth's atmosphere. Now, keep in mind, these distortions can occur anywhere in the atmosphere, from the very top of the atmosphere down to just in front of or even inside our telescopes. And again, I like this picture that I took long ago that well illustrates this. Notice that, yeah, the sun, as it's rising over the ridge, is heavily distorted, but the trees in the foreground are relatively sharp. So in this instance, the image distortion, the scene, was caused by high altitude atmosphere, not the near environment around the telescope. Now, the scene limits the resolving power at even the best sites on our planet to, well, pick a number, but I'll choose about 0.5 arc seconds, which again, if we assume our wavelength to be about 500 nanometers, that means that the 0.5 arc seconds is what can be resolved by a 250 millimeter or 10-inch aperture. We all know, in telescope size matters, of course. The more collecting surface we have, the fainter objects we can see. But larger aperture, as we said at the first thing to remember, larger aperture means greater resolution. And what do we mean by resolution? And of course, resolution is the finest angle on the sky that we can discern from its neighboring star or whatever. And that's encoded in the equation. The minimum angle resolvable is equal to 1.22 lambda over d. And that's if the angle is in radians and wavelength and aperture are in the same units, whatever that is. Now, if I convert that into arc seconds of resolution, not surprisingly, here we have resolution in arc seconds on the vertical axis, and on the horizontal axis, we have aperture along the bottom in meters, along the top in inches. Not surprisingly, as we go to larger aperture, our resolving power, the diffraction limit, as they say, of the telescope improves. Now down here at about an eighth of an arc second, that's about 5-inch telescope, we're already resolving 1 arc second. Half arc second, well, you're down into, can be resolved by a 10-inch telescope. Half arc second, or excuse me, a quarter arc second by a 20-inch, and on and on. Now, unfortunately, as we said, our atmosphere limits the resolving power to, well, again, pick your number, but I'll choose, even for an exceptional site on the Earth's surface, maybe a half arc second. So anything above this 10-inch telescope is not going to gain any further resolution because it's limited by that seeing limit of about a half arc second. Now, of course, what I'm saying applies to long exposures. Sometimes, yes, amateurs are now beating that limit by very, very fast lucky imaging and frame selection, that sort of thing, but we'll go with that as a definition. Now, an important concept is right at the point where the aperture critically samples the scene is what we would call the seeing scale, which goes by the name R0. Now, R0 you can think of as an aperture. So the seeing at your site can be thought of as the aperture that critically samples your scene. So that half arc second, okay, well, we would say an R0 of 250 millimeters or 10 inches. It can also be thought of as the scale over which the wave front coming into your telescope is effectively flat across there. So keep that in mind as well. We are not or the seeing scale. Now, when your resolving power is limited by seeing, your sensitivity, we all know, goes up as the square of the aperture. It goes as the area of your collecting area. However, if you're able to continue to be diffraction limited and increase your aperture, your sensitivity actually increases by the aperture to the 4th power. Now, why is that? Well, of course, seeing limits our resolution to a set enclosed area, whether that's 1 arc second, half arc second, whatever it is. That is the size of a unresolved image, say a star. Well, increase your aperture and you'll collect more energy, but it will still be limited to that enclosed circle, that seeing circle. So double your aperture, yeah, you have 4 times the collecting area, the image will be 4 times brighter. However, if you're able to maintain the diffraction limit as you go to larger aperture, your resolving power of the telescope goes up, and the enclosed circle of energy gets smaller. In other words, double your aperture, the airy disk is half the size. So from that, you get another factor of aperture squared. So instead of quadrupling, the energy density flux is increased by a factor of 16. So you can see that if you can maintain that, you win not only in resolution, but in the sensitivity of the telescope very, very quickly. Now, here's kind of a cartoon showing what we're dealing with. Above the atmosphere, we have essentially perfect seeing as wavefronts pass through a distorting and aberrating medium, which we call atmosphere. It comes through the previously flat wavefronts are distorted, enter the telescope, and we have a blurred image. Of course, we can solve that by launching telescopes above the atmosphere. And back in the dark ages, when I was an undergraduate, there was a truism that that was the only way to solve this. The problem, of course, is space is exceedingly expensive. Here's a typical example of a 6.5 meter telescope launched into space for only $11 billion. Now, my rule of thumb is space telescopes tend to be something of the order of 3 orders of magnitude more expensive than the ground-based equivalent. So yeah, space is expensive. Another option became adaptive optics. Now, adaptive optics, conceived of in 1953 by Horace Babcock up at Mount Wilson. And here's a shot of this seminal paper on the issue, which we'll discuss tonight, the concept. But try as they might with 1950s technology, it's just impractical to make work, and was, we thought, sort of forgotten about. But in secret, the DoD, starting in the 70s and 80s, did develop the technology in secret once high-speed computers became available. And a lot of the astronomers who were on that team lobbied heavily and realized the importance of this technology to astronomy, lobbied and got permission to mostly declassify the technology in 1991. Okay, so adaptive optics. The first misconception I want to address is the confusion between adaptive optics and active optics. Now, they are very similar conceptually, but are used for very different purposes and in very different time regimes. Adaptive optics is meant for high-speed correction of aberrations caused by our atmosphere. And for that, when I mean high speed, I mean something in the kilohertz range, several thousands of corrections per second. And typically, the actuators to do that are attached to a very thin, small mirror. The primary mirror, that large primary mirror, just has too much inertia to move at the speed necessary to keep up with the atmosphere. Active optics, on the other hand, is conceptually very similar, but is meant to correct for very slow aberrations induced into the telescope due to its own flexures as it slowly moves across the sky. So corrections can be far slower, something in the order of seconds as opposed to milliseconds. And typically in that case, the actuators are connected directly to the back of the primary mirror itself. Here's a picture of the mirror cell. Will physically control the primary mirror to keep it in the shape that they desire. Okay, now here is a cartoon showing the basic functionality of an adaptive optics bench. What we have is a essentially perfectly flat wavefront coming in, passing through the atmosphere, becoming aberrated into some random wiggly wobbly shape. In here, we kind of assume there is a telescope that takes a collimated beam in, sends a collimated beam out. And the first thing that the aberrated wavefront hits is a deformable mirror that has been moved into the proper shape that just corrects for and cancels out that wavefront distortion. So coming off that is a relatively flat wavefront that is sent on through some re-imaging optics onto our science camera. And if designed correctly and working beautifully, down here you might be actually resolving the diffraction limit of that telescope. At the same time, some of that light needs to be picked off either by a beam splitter or a dichroic, something like that, to send some of that energy off to a unit that can determine, a wavefront sensor that can determine what that wavefront distortion is in real time. That is then analyzed by a computer that decides what voltages need to be sent to the actuators on the deformable mirror, goes through amplifiers to the actuators itself, which then drives the mirror to the next shape to take out the residual error as the wavefront is continuing to evolve. Very straightforward, fairly conceptually. However, keep in mind, this is a continual closed loop servo cycle that needs to go faster than the sky has a chance to change. Now, one interesting note, AO doesn't really know, nor does it care where these aberrations come from. And if the Hubble telescope had had AO from the start, there never would have been a problem. It would have seen an aberration, it would have taken care of it, and no need for that $250 million delivery fee for a new lens. Now, the deformable mirror, let's talk a little bit about that. Well, the deformable mirror is typically a relatively small and thin mirror, something on the order of maybe 1 millimeter thickness that is thin enough to be flexible to some degree. It's sometimes maybe referred to as a rubber mirror for that reason. Now, here's a commercial example from a company called Zenetics that is, it's about 100 millimeter flat mirror with 394 actuators behind it. Behind that mirror is a matrix that push and pull on the mirror in real time to take it to the shape that's desired. On the right, we see a much larger example. This is the secondary mirror from the large binocular telescope. I forget, do you remember how the aperture, that's like a meter across?
Yeah, it's
So
pretty big.
it is something of the order of a meter, I don't recall exactly, with 672 voice coil solenoids on the back for the same purpose. So again, the typical actuators are piezoelectric pistons or small voice coil. The point is that it is small, much smaller than the primary mirror, does not have the inertia of that big primary mirror, so that these actuators can adjust it very quickly. And there are even very small deformable mirrors. Here's a example of a broken deformable mirror. The person who broke it shall go nameless, although when he left the observatory, they gave it to him as a memento. When this was functional, it would have had a nitrite membrane over the front with a reflective surface. The nitrite had a ground potential on it, and I don't know, hopefully you can see this. There are the sites on there which one could vary the static voltage on, which would give a tug to that membrane in front. These are and be able to be used as a small adaptive optics mirror with only 37 actuators as opposed to 349 or 672 below. But such things as this can be had relatively inexpensively. These are a few $1,000s as opposed to hundreds of thousands of dollars. Now, recall what I said before is that any arbitrary wavefront distortion can be corrected with additional optics. An image of the telescope pupil, that is the primary mirror itself, formed on the deformable mirror. And then changes made to that deformable mirror are equivalent to if we made those changes to the primary mirror itself. So distorting the deformable mirror is equivalent to distorting the entire mirror, but very, very quickly. And a mirror with the same curvature, but half the amplitude, will reflatten the reflected wavefront coming off of it. Now, common misconception comes from the word canceling the curvature or the distortion, I think. So a common misconception is to cancel that, you really want the opposite curvature from the wavefront. Now, that's really not the proper solution, and I have a little illustration here that I hope will convince you of the correct solution. Now, imagine we have a cut across a highly stylized, rather contrived, overly simplified, grossly exaggerated wavefront here that is a step function. Of course, you'd never see a wavefront like this, but this is easy to draw and I think illustrates the concept well. That wavefront, imagine that is propagating downward towards a mirror surface at the bottom of our screen here. Now, of course, I think you can figure out what's going to happen is that aberrated wavefront reflects off of that mirror surface. It reflects off with precisely the same aberration as it started with, just inverted, the mirror image, so to speak. But we didn't really alter it in any way. Now imagine, as intuition might dictate, we try a deformable mirror that tries to cancel that aberration by creating the opposite wavefront shape. So here we are with the same wavefront, but this time we have a deformable mirror. The computer senses that wavefront and creates the opposite shape. And now watch what happens. Not only did we not correct the wavefront aberration, we inverted it as with the flat mirror, but it's now twice the amplitude. Clearly, that's not the solution. Now, just for completeness, let's maybe try reflecting off a mirror with exactly the same wave shape. And here we have again, the deformed mirror takes on the same wave shape, but now the entire aberrated wave front comes into contact with the mirror simultaneously, lifts off, and what we end up with is, again, exactly the same aberrated wave front. So that's clearly not the solution either. But maybe you've already realized that, let's think about this. This using the same wavefront does nothing to the wavefront aberration at all. A flat mirror gives us exactly the same wavefront, but inverted. Perhaps what we want is the right halfway in between those extremes. So let's try that. Here's a mirror, deformably mirror takes on the same shape, but half the amplitude, and let's watch what happens. Now, as the wavefront comes down, the lowest part reflects off the lowest part of the mirror, and is just passing the next lowest part of the wavefront as it reflects off the next lowest part of the mirror, and the last part reflects together. And congratulations, there you go. We have corrected the wavefront aberration. We have a flat wavefront. We can send that through re-imaging optics, and we have corrected to the diffraction limit of the telescope. Congratulations. Well, maybe you aren't completely convinced or think in wavefronts. Maybe it would be worthwhile to do a very quick illustration of that you can think of this in ray space as well as wavefront space. So here's another aberrated wavefront coming down. Now, here are rays. What are rays? Rays are simply projections at every point across the wavefront that are normal to the wavefront. So here's a selection of rays. And if we reflect that off of a surface that has, again, the same shape as the aberrated wavefront, but half the amplitude, let's take a look at how one of those rays reflects off of there. Now, since the incoming ray has twice the angle of the reflecting surface, and it reflects around the normal, the returning ray comes up vertically, which is basically what we want. If, on the other hand, we have the opposite shape to cancel that wavefront, the ray shoots off towards the side of our screen and is clearly not the solution we want. Yes, this is the solution we want, which is the half angle or half amplitude of that wavefront across there. If we apply that to all the rays, every ray comes up vertically, and again, we end up with a nice flat wavefront. So here we are back with our cartoon of the adaptive optics system. Let's look next at that magic black box called a wavefront sensor. Excuse me. Now, there are a few different types of wavefront sensors go by the names like Shack-Hartman array, pyramid, wavefront curvature. But the only wavefront sensor I have direct experience with, and as far as I know, is by far the most common type, is the Shack-Hartman array. What is a Shack-Hartman array? But it is a array of small lenslets. So a small lenslet array in a two-dimensional arrangement. Now, this optic on the right, that's actually about a 2-inch optic, and each of those circles is a separate lens. Now, if we place those lenses in a pupil image, or place a pupil image of the telescope on that array, each lenslet will image what that part of the telescope pupil is seeing, what that part of the primary mirror is seeing. Now, if each lenslet subaperture is less than that seam scale that I was talking about before, the R0, where you are critically resolving the seam, if that is less than that, then each of these lenslets the images will be diffraction limited for its effective aperture, and each image will be identical, except for displacements due to image motion. There will be, the wavefront can be thought of as flat across that aperture, but it still can be tipped or tilted, which will cause the image to be displaced. This cartoon over on the left illustrates that nicely. If you have a perfectly flat wavefront coming in, identical image will be imaged behind each lenslet at the same location behind the lens. However, if it is a distorted wavefront, it will be displaced off to one direction or the other, depending on the curvature of the wavefront. And by measuring that offset, one can work backwards and reconstruct the wavefront distortion. Now, here's an actual Shack-Hartman array from my ex-employer out of Big Bear. And we're looking here at a sunspot. So you can see that everywhere across the telescope primary mirror, we are using a lenslet to reimage that sunspot in each subaperture. However, if you look in some of the different places, like over here on the edge, you'll see that the sunspot is displaced upward. Down maybe here, the sunspot is displaced lower, maybe here to the left a little bit. And that is compared to a reference subaperture. What is typically done is one subaperture near the center, the image from it will be recorded and saved and used to compare that against each subaperture to then remap or reconstruct that wavefront distortion. So what does a Shack-Hartman or a wavefront sensor actually look like? Here again, most of my illustrations are from Big Bear because that's what I had access to. Here is the wavefront sensor for Big Bear. It's just a CCD, just a stack of optics. As I recall, I think this mount held the Shack-Hartman array. Here was a lens that formed the pupil image on there, and which then formed the lenslet array images back here on this high-speed CCD. So just a bunch of optics. And here again is another image of an actual Shack-Hartman frame taken a couple years ago in November 11th, 2019, as Mercury was transiting across the solar disk. And again, here is the reference wave subaperture, which is that one there saved up in the corner. And then its position is then compared to each subaperture across the entire pupil image or mirror image of the telescope. This is just a cross correlation determining where the center of that image really is. Now the reconstructed wavefront is then fed back to the DM, which then corrects the actual image. And here is an actual frame taken of that Mercury transit, again, November 11th, 2019. Here's the planet Mercury, here's the surface of the sun. And you can see we are diffraction limited even for a 1.6 meter telescope there. So how well does adaptive optics work? Well, pretty well. Here is a typical, rather poor seeing day at Big Bear with natural seeing, adaptive optics turned off. If you turn on adaptive optics, and I hope this video is coming across fairly smoothly, you can see the dramatic improvement possible. Now each frame in here is, what is actually done is 100 frames are collected very quickly, and then in post-processing, the computer program using a technique called speckle reconstruction is actually able to go through that stack of 100, pull out the finest resolving power example through there and reconstruct the image here. So this is a phenomenal image of solar granulation taken again at Big Bear. And how do we actually determine what is fed back to the VM? Well, the wavefront is fit to a series of equations of ever increasing exponential order. Each equation represents with a complex shape of the wavefront. The number of modes, and these are often called modes, these exponential equations. Each one is called a mode. And the number of modes is, of course, limited by the number of deformable mirror actuators. One common exponential series is called the Zernike polynomial series for the mathematician who originally came up with it. And it is it's a popularly used polynomial series because each polynomial describes a physical optical aberration of ever higher order. Now, when I say higher order, I mean higher exponential order, but what it really physically translates to is basically more humps and bumps on the aberrated wavefront. So lowest order, which are linear, of course, or just tip and tilt. Second order might be defocus. Astigmatism is a second order. Jump up here to trefoil, which is a third order. Quadrifoil, fourth order, and on and on and on. Now, before you panic about all these equations, let's just make them go away and don't think about the fact that they are even there. Just realize that the computer, when it was originally programmed, somebody had to look up all those series of equations, program those in such that the computer can recognize them. Now, in reality, often a very large fraction of seeing is just in image motion, which translates to tip and tilt of the wavefront. So often in a real adaptive optics system, tip and tilt will be separated out to a separate high-speed flat mirror and corrected independently, so that the actual deformable mirror, the amplitude of the deformable mirror is saved to be able to correct the higher order aberrations. Now, as kind of an example of how this might work, here is yet another highly contrived cartoon example I've drawn up. Imagine again, we're looking across an aberrated wavefront coming down. And of course, what we're doing here would, in reality, need to be done in 3 dimensions, not 2 dimensions, but I think it illustrates the concept. So here is an aberrated wavefront. What we would first do is do a linear fit to that, whatever that waveform is. In other words, fit a line to it. Then that line could be subtracted out and left with that. Then we could fit the residual to a second order polynomial, subtract that out, and then fit that to a third order, subtract that out. And you can see very, very quickly that we can get to a point of diminishing returns rather quickly in this. And here we are with just a fourth order fit to this thing, so taken out, and you can see the dramatic improvement. There are still numerous wiggles, which would take a much higher order to take those out, but perhaps for your telescope optical system, maybe we've already corrected enough, or maybe this is all the actuators you have, but you can see that rather quickly you can make improvements to that aberrated wavefront. Now, of course, we would not physically subtract out one waveform at a time. What we would do is mathematically is model that, subtract that from the image, fit all these different polynomials to it, then sum up what really needs to be sent back to the VM at one time and correct them all simultaneously. So how do we determine what the image displacements are? Well, for point sources like natural
Agree
stars.
100%.
Excuse me, do I have a question? Okay, I guess. For point sources like natural or laser guide star, simple centroiding, which is fairly easy to understand, can be used. However, for the sun, or other extended objects, it's a much more complicated and less intuitive problem to try to figure out how something like this, where the center of that is or how they match up. For that, some kind of cross-correlation technique must be used. Now, there are numerous types of cross-correlation, but in my opinion, the easiest to understand and most intuitive is something called the sum of the absolute differences, or SAD. So here we have, just one more of my overly simplified cartoons. Imagine, as I said, we've taken a reference image at the center of the Shack-Hartman. Now, here we are taking a cut across that, and this way we're not looking at position, but we're looking at intensity, pixel by pixel across that image. Now, again, of course, in reality, we would need to do this in 2 dimensions, not 1 dimension. But again, for simplicity, I think this illustration works. So here is pixel by pixel. This pixel sees an intensity of 4, 5, 5, 8, 7, et cetera, et cetera. Now, let's compare that to one of the other subapertures. And again, as I said, if properly designed and the subapertures are effectively smaller than your seeing scale, that are not, again, then the images should be effectively identical. Of course, there will be small aberrations, things like that, but for all intents and purposes, call it identical. So now go pixel by pixel and count and add up the sum of the differences between these 2 images. In other words, at this pixel, there's a 1 count difference here, 2, 0, 1. Now we're not just subtracting one from the other, it's the absolute difference. So no matter which one is higher than the other, it is the difference between them we're looking at. So then we come up with some difference pixel by pixel across there, sum those up, and we come up with a number. In this case, it looks like something like 35. Now, mathematically, let's shift that subaperture over 1 pixel and repeat the process. Sum up the difference between them, pixel by pixel across there, and we come up with a value. In this case, it looks like 24 maybe. Shift it again, and we come up with a total of 21. And at the point that those 2 images overlap, we go to a minimum. In my idealized case here, we go all the way down to 0, but of course we'd have noise, and in the real world, it wouldn't go all the way to 0, but it will be a minimum. Keep going out the other way, and again, we get a worse and worse correlation between those. So, and again, this is 1-dimensional, but I think it gives the feel for how that can be done. In reality, we would need to do that in 2 dimensions, where we move that array across to the point where those 2 images overlap and the difference between them goes to a minimum. And from that, we can find out the vector offset, how we have to move to get those back where we are and use that to know what the offset is for our wavefront error. And now, how do you calibrate a deformable mirror? Now, adaptive optics, what we are doing, of course, as we keep saying, is we're taking an aberrated wavefront down, and out of that, we're creating a sharp image. To calibrate the system, we kind of do the opposite. We work backwards. So what we do is at a image plane inside the telescope in the AO system somewhere, place a pinhole. That pinhole will define where the actual image plane for the telescope should be by definition. And being that it's a pinhole, it will define a perfect image. In other words, once that's recollimated, a flat wavefront. And assuming that the DM is flat, from the manufacturer, then you will still, of course, probably see slight deviations from subaperture to subaperture where that pinhole actually is, but that would be due to manufacturing defects in the Shack-Harpin array. Okay, well, all we have to do is say, well, this is a perfect image. That's where a flat wavefront is mapped onto the Shack-Harpin. Great. Then we need to determine what voltage actuator by actuator on the mirror is required to create each of those aberrations, each of those Zernike polynomial aberrations, starting with tip and tilt and defocus, et cetera, et cetera. That sounds like a complex thing, but it is, and it would be an iterative process, but keep in mind, it does not need to be done in real time. It can take as long as necessary. You could even imagine just sitting there with a whole bunch of knobs and diddling the voltage on each actuator until you come up with the proper wavefront distortion that you're looking for. Now, once you have that, you just need to record what the voltages are that makes each of those aberrations. And then once we are done and actually working, the computer knows how to make each aberration. All we have to do is, when we map out those aberrations from the actual wavefront, is know what the amplitude is. One number per aberration, feed that into the computer. The computer then multiplies it knows how to make that, but now it just needs to multiply by the amplitude change to create the actual aberration and correct the wavefront. I hope that made sense. Now, that would be the ideal case if the actuator was truly linear with voltage. That's probably not the case. It probably is not, but we can also calibrate each actuator by running it through its entire range and coming up with a displacement versus voltage, displacement as a function of voltage for each actuator. Now, all that sounds like a lot of math. It actually is, but it's simple math, and computers are very good, and unfortunately, computers are exceedingly fast and can do all those calculations necessary in real time to keep up with the incoming wavefront distortion. Unfortunately, bright stars, we need to sample these things very quickly, so we need a bright reference star where we're looking on the sky. And unfortunately, bright guide stars are fairly rare and usually not conveniently placed right where we want them. So that led to the development of what's known as laser guide star. And there are two types of laser guide stars. One called sodium laser, which uses a sodium laser at a wavelength of 5892 angstroms. And that laser is shot up in the in your field, in the center of the field, and excites sodium atoms at the very top of the Earth's atmosphere. It's about a roughly 5-kilometer thick layer just below the carbon line at 90 kilometers up there. So it produces a nice star-like feature at the top of the atmosphere. So it samples the entire aberration of the atmosphere coming back down through it. The other type of laser system is called a Rayleigh beacon. And it just scatters off particulate in the atmosphere, which of course samples or biases towards the thicker lower atmosphere, and so does not integrate through the entire atmosphere equally, which makes it inferior in that regard. However, if you're trying to image something in that sodium wavelength, this is another option. Also, Rayleigh beacons are simpler and cheaper to build, so there is a trade-off. Basically, just remember, if it ain't yellow, it ain't sodium. Okay, so how many lenslet subapertures or DM actuators are really necessary? Of course, it depends on your local R naught, how large of an aperture can remain diffraction limited and critically sampling that scene, and of course, your actual telescope aperture. In other words, let's take an example. Again, I'm still saying that our wavelength is in the middle of visible, which I'm calling 500 nanometers out in the green. Say our scene in this case is 1 arc second. So if we solve that for R naught, that comes out to an R naught of 125 millimeters or 5 inches. In other words, if you had a 5-inch telescope, your 5-inch telescope would be diffraction limited under 1 arc second scene. And there's no reason to have a high order adaptive optics system. Tip tilt would be all that's needed, and you're done. Either that or just take very fast images and register them after the fact. But say you had instead of a 5-inch telescope, same very good scene, you had a 15-inch telescope. Well, in that case, you would need at least a 3x3 matrix of subapertures and actuators on your deformable mirror, making a total of at least 9 to be able to reconstruct the diffraction limit under that very good scene. Keep in mind, of course, the R naught can change and will change moment to moment. So when we talk about R naught, that's usually an average for the site. Now, of course, the good news is small telescopes don't need very many subapertures. And as I said, if you're at or below the R naught, you don't need any. Also, at longer wavelengths, the resolving power of your telescope goes down, and seeing is actually better, which results in a larger R naught, meaning you need fewer subapertures, fewer actuators, all that sort of thing. Still, actually, the number of actuators goes up again as the square of the aperture. So double the number of double the aperture, and you quadruple the number of actuators necessary given the same wavelength and seeing. Why do I say that the seeing gets better as you go into the red to longer wavelengths? Well, here we see the Rayleigh criteria again of, but in this case, we're going to keep the aperture set, but increase the wavelength we're looking at, going further into the red. So as this number goes up, the resolving angle gets larger and larger. So yes, as we know, the resolution of our telescope gets worse as we go into the red. But also the seeing does actually get better. And that is because refraction decreases. This is known as dispersion, as well illustrated here by the eminent Professor Pink Floyd. Short wavelengths, blue, violet, are more strongly refracted than the longer red wavelengths or infrared wavelengths. So as you go to longer wavelengths, the deviation of the rays through those seeing bubbles, those seeing cells passing through your field, are decreased. So the R0 scales a little more quickly than you would assume just by the resolving power of the telescope, which scales a little more quickly than linearly, something like the wavelength to the 6/5 power. Or in other words, if you double the wavelength, the R0 is not 2 times larger, but something like 2.3 times larger. So yeah, out in the infrared, adaptive optics becomes less critical, simpler to build, etc. So how fast must corrections be made? Well, again, that keeps coming back to the R0 and the telescope aperture, but also the wind. How fast are these aberrating cells coming through your field? That's something that really needs to be measured empirically for each site and characterized. But in essence, the system has to work fast enough such that it can beat the change in the atmosphere. It needs to be able to correct faster than the sky has a chance to change. Rule of thumb, somewhere in the kilohertz range. Big Bear, for our 1.6 meter telescope, we worked at about 2 kilohertz. And so again, it depends on the site, etc. Now, very importantly, the limitations. Of course, if the amplitude of a wavefront coming in is too great, it will be larger than perhaps your deformable mirror can actually form and correct. That doesn't mean that the adaptive optics system can't still help. It just means that it will not be able to fully correct for that wavefront distortion. And a big one that is often glossed over when, at least in the media, is the fact that we are correcting for one point on the sky. We are measuring the wavefront correction coming from our laser guide star, the sun, whatever. At one point, we're measuring the wavefront coming in there and correcting for that. Off through the side, the light coming from that will be coming through a different part of the atmosphere and will have a different wavefront aberration. So we find that the size over which the image is corrected is limited and actually can be very small, maybe only a few arc seconds across. The region that the correction applies to is called, for a cool name, the isoplanatic angle. Iso meaning same, planatic meaning the same flatness. It can be tipped and tilted, but we can consider it flat over that area. And of course, the number of subapertures and deformable mirror actuators scales with the square of the aperture. And I should also point out that on the deformable mirror, you would need at least twice the number of actuators of subapertures that you're using, because within each subaperture, you need to correct for both tip and tilt. And of course, you can only correct to the diffraction limit, to the limit of what your optics can deliver, if the subapertures are effectively smaller than your R0. So finally, what's coming in the future? Where are we and what's the cutting edge here? Well, now we're moving beyond what is called classic adaptive optics onto something called multi-conjugate adaptive optics. Multi-conjugate adaptive optics, I'm not going to go into detail, but it uses multiple deformable mirrors which correct for discrete, separate atmospheric layers independently. Now, this does not lead to an improvement in image, but it takes that corrected area and makes that applicable to a wider isoplanatic angle. Now, if you watch this movie here, again from Big Bear, the MCAO system there, you see the corrected area with classic single DM. Now switching to multi-conjugate adaptive optics, you could see that what was correcting over maybe 3 to 5 arc seconds is spread out to several times that diameter. Again, here we are with a few arc second resolution or correction in the center, classic AO. Now switching to multi-conjugate adaptive optics. Multi-conjugate adaptive optics is, as you can imagine, much more complex to try to get all these things to work together. But as we go to ever larger telescopes, we will need this technology to enable these gigantic multi-segment mirror telescopes. And another paper that came up recently is the idea of using predictive algorithms to decrease the correlation lag. Now you can imagine one limit of adaptive optics is you measure the wavefront distortion. It takes some time to analyze the wavefront sensor, determine the amplifiers, drive those, and then actually drive the DM to the correct wavefront. And in that time, the sky is changing. It would be the lower the latency time there, the better correction we can do. So this paper is looking at ways of maybe being able to have predictive algorithms of what the wavefront is going to do. Think of the fact that the wavefront is kind of getting steeper. Well, yeah, in a moment later, you can probably assume that it's probably going to be a little bit more steep. At least it's not going to be a huge discontinuity and start calculating from a completely flat wavefront again. So by looking at the rate of change, where we were, and making some predictions about at least where we are and what may be coming after that, one can possibly cut down in that lag time between detection and correction. And just a couple of days ago, I came across this, a wavefront correction using something called a spatial light modulator. Now, this is a liquid crystal on silicon. Liquid crystal has the property of being a wavefront retarder. So, and a active liquid crystal can vary the amount of time delay a wavefront will see as it transits through the medium. So you can take that aberrated wavefront and the wavefront that is ahead of the back part, you could have that part of the liquid crystal slow that part of the wavefront down, and by the time it re-exits the liquid crystal, flatten the wavefront that way instead of using a deformable mirror. Now, apparently these things are not all that fast, but they already have a very high pixel count. The largest I saw was 1900 by 1200, which could make this applicable to very large telescopes. Or if these things, it looks like maybe these things can be produced much more expensively in the future with semiconductor technology. So maybe this will push the price of adaptive optics down into the future. And finally, the question that's burning in all your minds is, when can I get this for my backyard telescope? Well, as I've said several times, if you have a reasonable sight, your R0, your telescope aperture is probably not that much larger than your R0. And a large component of that seeing is likely tip and tilt. So already there are tip tilt correction units that are available. They're reasonably affordable and they are effective. I noticed, I think SBIG, Orion, Starlight Express all have these, what they call adaptive optics, but I would call an image stabilizer stage, and they are effective. Higher order adaptive optics, taking out higher order aberrations, they're still a bit expensive. Here's a benchtop demonstrator from Thor Labs that's $12,000. Akko Tech that for flexible optics that made this deformable mirror. They built one. I don't know what they sell that for, but they're still expensive. They're finicky to use for the amount of improvement we probably get. So I think we're a ways off from having high order adaptive optics available for our telescopes, but these tip tilt units are quite effective, and hopefully the prices will continue to come down on those. So thank you very much. I hope you stuck with me, and if I haven't used up all my time, I'm happy to take questions. And while there, here's a vocabulary list you can use to impress people at your next cocktail party.
Have you used adaptive optics anywhere besides the solar scope at Big Bear?
Well, my experience is all from my career, which was all in solar astronomy, both at Big Bear and back at the National Solar Observatory and at Kidd Peak, the McMath Pierce Solar Telescope. So my personal experience is there. At Big Bear, the only use was on the sun. I did build a couple of adaptive optics benches back at the McMath Pierce telescope. One was used on the sun and one was actually used for the planet Mercury. But I do not have direct stellar experience with AO systems.
That's very good. I mean, it's amazing, this stuff that, like you said, 50 years ago, and what we had, and you just imagine what's coming.
Yes, 10 years ago, they were talking about extreme AO using extremely high number of actuators, DMs, things like that, and sub-apertures for being able to resolve exoplanets, things like that. So that's only going to continue. And somewhat timely for tonight, it was mentioned that, of course, James Webb has deployed all its mirrors and is now adjusting all those mirrors. What we're talking about there is active optics. And of course, in space, they normally don't deal with adaptive optics, but active optics, I think, will become ever more important on these large, ultra-thin telescopes, both on the Earth's surface and in space.
Thank you very much.
One thing I was wondering about was any impacts or changes to the materials that are used in mirrors, for the mirrors or lenses when you're dealing with adaptive optics. I would think that maybe some materials are better than others when it comes to, moving them around with actuators.
My experience has only been with borosilicate, which I think is fairly flexible and not that rigid. I don't know about too many other materials. Again, this small membrane, the membrane that would have been over the front of this thing was a silicon nitride that was then aluminized to make a reflective surface membrane. So I could imagine other flexible materials. I did hear a talk once by Thomas Rimley out in Hawaii of developing an active mirror surface using synthetic muscle, a material that contracts under a current. So, yeah, who knows where we're going with that?
Yeah.
And again, even that liquid crystal technology was something I just ran across a few days ago, trying to get this talk up to date.
Yeah, thanks for your answer there. Appreciate it.
Anything else? Okay, well, thank you very much. I appreciate the opportunity.
That was great. Thank you.
Thank you. That was fantastic.
Yeah, thank you very much.
Appreciate it. Thank you. Have a good evening.
It was great.